Alright, look here, these are the three famous SUVAT equations, also known as the equations of motion. We're going to plot them out in graphs, and we'll see what they look like. So let's start with the VT graph. For ease of discussion, let's assume that the motion is along a left-right line, and let's take rightward to be positive. So if both U and A are positive, then the motion will be going rightward at a faster and faster speed. If both U and A are negative, then the motion will be going leftward at a faster and faster speed. If U is positive but A is negative, then the motion will slow down before it speeds up towards the left. If U is negative but A is positive, then the motion will slow down before it speeds up towards the right. But no matter what, you notice all these are straight line graphs. So in uniform acceleration motion, the velocity always varies linearly with time. Alright? Now, the graph we are most interested in is actually the one where U is 0. So the equation reduces to V is equals to A times T. And this is what the graph will look like. So since U is 0, the straight line graph must pass through the origin. The gradient of this line is, of course, the acceleration, and the area under the graph is the displacement. At equal units of time, the velocities will show a very simple arithmetic progression, That's because the velocity is increasing linearly with time. But there's something even more interesting. If you look at the distance completed during equal intervals of time, they actually also show an arithmetic progression, During the first second, it completed 1 unit distance. During the second second, 3 units. During the third second, 5 units, and so on. If it's not clear to you that these areas corresponds to 1, 3, and 5 units of area, maybe I'll chop it up into equal triangles for you like this. Now you can see, right? This is one triangle. This is 1, 2, 3 triangles. This is 1, 2, 3, 4, 5 triangles. Okay, let's move on to the ST graph. So again, if both U and A are positive, then you'll be traveling rightward at a faster and faster speed. If both U and A are negative, then you'll be heading leftward at increasing speed. But if U is positive but A is negative, then you will head rightward before you make a U-turn, and then you go leftward at increasing speed. If U is negative but A is positive, then you at first head leftward, come to a rest before you make the return journey, and then you'll be heading rightward at increasing speed. Notice that all of them are curves. When acceleration is constant, the ST graph are always quadratic segments. Again, the graph we are most interested in is when U is 0. So the equation reduces to S equals to half AT squared. So the gradient of the ST graph is, of course, velocity. So that's why the graph will get steeper and steeper over time. But because U is 0, the graph has to start with a flat gradient, because you started out with initial speed of 0. If you look at the displacement at equal time intervals, you see the square numbers progression, 1, 4, 9, 16, 25, and so on. Okay, what about the VS graph? So if both U and A are positive, you'll be heading rightward at increasing speed. If both U and A are negative, then you'll be heading leftward at increasing speed. If U is positive but A is negative, then you'll be heading rightward but at decreasing speed. Come to rest here before you make the return journey, so now you're heading leftward at increasing speed. If U is negative but A is positive, then you'll be heading leftward first but at decreasing speed. Comes to rest before you speeds up towards the right at increasing speed. Again, the graph we are most interested in is when U is 0. In that case, then the equation will just reduce to V is equals to square root of 2AS. So it's just a square root graph. It's a square root graph. So because it's a square root graph at equal time intervals, the velocity is actually 1, or rather maybe square root of 1, square root of 2, square root of 3, and so on. Also, there's something special here. Note that the gradient at the origin is actually infinite, right? Infinity. That's just what the square root graph looks like, right? Yeah, but can we make some physical sense out of this graph? Yeah, we can, huh? So why does it have this shape? Because a lot of students say, isn't the acceleration increasing at a constant rate with time? Yeah, you're right, with time, you know, but what we are plotting here is with respect to displacement. In fact, because the speed is increasing continuously, so it will always take a shorter time to complete the same distance compared to earlier. Get it? So it's going to take a shorter and shorter time to complete this, then to complete this, and then to complete this. So since there's a longer time here, you've got the largest increase in velocity here, and as the time intervals get shorter and shorter, the velocity increase also becomes smaller and smaller. That's why the graph that is not a straight line graph, but rather is a curve that becomes flatter and flatter. And the math tells us that it's exactly a square root graph. Okay, I hope that you found that interesting. That's all. Ta-ta!